Hello everyone, welcome to PCT Lecture 10. Today we will discuss power system stability. It consists of swing equation, power angle equations, power angle curve, and then we will use equal area criterion to find out critical clearing angle and critical clearing time. The power system in their normal operating state, it works as a synchronous system. So for example, in our daily life, we work with 50 Hz electricity. So everything in our system have to synchronize with that 50 Hz. Um, if you are at the sending end, the generator will rotate and output 50 Hz electricity. If you are at the receiving end, you also receive that kind of 50 Hz. So if we plug something in the middle, let's say a new load or a new generator or motor, it should be able to synchronize with the system. And hence, our stability studies need to evaluate the impact of those disturbances on the electro and mechanical dynamic behavior of the power system. To be able to do that, we need to simplify our system by making assumptions. So there are three major assumptions here. First, only synchronous frequency currents and voltages are considered. So essentially, our DC offset and harmonic components are all neglected. Second, only symmetrical components are used. And third, voltage of electrical machines is considered unaffected by speed variation. So during our analysis, we assume that it stays constant. So first we look at the behavior of a generator. For example, this generator rotates with the angular speed of omega, and the mechanical torque applied to it is Tm in the same direction with omega. And the winding of the rotor or the machine will generate a electrical torque in the reverse direction of omega. So here is the equation showing the relation between the movement of the rotor and the torque applied to it. J here is the moment of inertia of the rotor. Theta is the angular displacement of the rotor referred to a stationary frame which doesn't move, and T here is the time. So if we convert this one to a new form, then we can rewrite it as this formula. We also express the same relations, but here we have H is the inertial constant of the rotor, which is megajoule over mega VA. This one expresses the relation between the kinetic energy of the machine or the rotor in comparison with the base power of a system. The PM and PE is the power that apply to the rotor, which is also there also in PU. Delta here is the angular displacement of the rotor, but this time it refers to the rotating frame of omega t. T here is also the time. So this one we call this the swing equation, and this swing equation will be used to analyze the behavior of the rotor of an electrical machine. Next, we look at a single machine on a infinite bus. This infinite bus is the one that has constant frequency and voltage, regardless of the condition of the transmission line. So in this case, we can rewrite the schematic as this one in PU expression. So get rid of the transformer here and replace it with a reactance. The generator will be expressed using a voltage source and a reactance of Xg here. So everything in combination, we have a equivalent reactance of Xg plus Xt plus X line here. We assume that we take the V-bus as a reference with zero angle, and the Vg here will have a phase angle of delta. So we can calculate the active power at the sending end or at the receiving end by reviewing lecture 2. Here we have PE equal Vg times V-bus over X EQ psi delta, or it is P max psi delta. So next we compare the swing equation with the power angle equations. So here is the result. On the left hand side, we have the expression that show the change variation of our delta over time, and on the right hand side we have the power of the mechanical and the electrical power. If we plot it, we see that the electrical power will be like this. So this is the P max times psi delta. You take this shape, the horizontal axis is the angle, and the vertical axis is the power. This power will be compared with the mechanical power here. So for example, our mechanical power PM is here. So we assume that at the beginning it stays stable. So PM equal P max psi delta at this point, X, and it's balanced. Next, we assume that there's a certain change and the power of the mechanical side change from PM to PM1, which is higher. In this case, looking at the equation, d squared delta over dt squared will be positive, and therefore the rotor accelerates toward delta 1 here. So it accelerates. So at this point, y, the PM1 become equal with the PE, which is P max sine delta 1. But it doesn't stop here, because here it has some speed and kinetic energy. So it continues to increase delta to delta 2, which is at the point Z here. And here at the point Z2, PM1 is less than P max times sine delta 2, so PM1 is smaller than PE. So next, it needs to form back to the initial point, because here our right hand side will be negative, and therefore the d squared delta over dt squared will be negative. So it decelerate back to y, and then it continue to decelerate to x, and then it oscillate around y. In this case, we look at our equal area criterion, which says that in this case A1 will equal A2 because the kinetic energy gain will be equal to the energy loss during deceleration. Here we assume that there is no loss in the winding or in the system. So the system will oscillate around y like this. So we know that when we increase the input power from the mechanical side suddenly to PM, for example, then the rotor will start to move from position X to Y, and then continue to go to Z. If Z is not the balanced position, then it will swing back and oscillate back and forth around Y. During the oscillation, the equal area criterion say that A1 and A2 will be the same because of the energy loss will be equal to the energy gain. If somehow Z is the new balance position such that PM equal P max multiplying with sine delta max. Then Z will become the new balance position and the oscillation will stop here. So this happens when PM, this line, meet the curve here, and it happens when delta max equal to pi minus delta 1. The equal area criterion is used to define A2 and A1, and therefore the position X will be defined depending on this. So this will be used to find out how to start or to accelerate a motor or a generator without causing oscillation in the system. So next we discuss the stability during a balanced three-phase fault. For example, we look at this system which has a generator connecting via a transformer and then have a transmission line connecting it to a infinite bus. If we neglect the resistance of the transformer and the generator PE is 0 during fault, for example we have a short circuit here, then the voltage of this will be 0 during the fault, and therefore during the fault the power PE in the system will be Vg times V here over the X of this part. It will be 0. So at first we start with the X position where we have the PM equal PE, but suddenly the PE becomes 0, and then our swing equation pointed out that our rotor must accelerate from delta 0 to delta 1, which is here. And if we assume that S delta 1, the fault is clear, and PE takes the value according to this position, which is P max times sine delta 1. Suddenly we have the situation of PE is higher than PM. So the rotor decelerate to Z here, because now we still have the speed of the rotor, so it's slow down and stop here at Z, and then it will return to X, and then we have the system oscillating around X. Now we don't want that to happen. What we want is that when we clear the fault, the system will start from Y here, decelerate to Z, and stop at Z. So the condition of stopping at Z is that PM here will equal the new electrical power P max times sine delta max. So this occurs when we adjust the delta 1 in the middle to be delta C, which is called critical clearing angle, so that the area A1 here will become this area A2. So this occurs when delta max is determined by this PM line, and it will be pi minus delta 0. And delta C, the critical clearing angle, will be given as cosine delta C equal cosine delta max plus PM over P max times delta max minus delta 0. So here we can find out delta C by taking the arc cosine of this one. Next, the critical clearing time Tc is the time that needed for the rotor to move from delta 0 to delta C. We need to know this one because we need to operate the switch to restore the system right at delta C. So this DC will be square root of 4h times delta C minus delta 0 over omega times PM. So next, let's have a look at a numerical example. Here we have a 50 Hz system. There's a single machine generator connecting to a infinite bus. It sends power to the infinite bus and the power is given here. The bus is infinite and the voltage is constant at 1 pu. All the parameters are given. Now we have a voltage symmetrical fault occurring here in the middle after the transformer. After the fault, the system will be restored to normal using circuit breakers operation. Our job is to find out the critical clearing angle and critical clearing time so that the system will remain stable. So first we draw the equivalent circuit. So the generator will be redrawn as a voltage source Vg in series with a reactance XD prime. The transformer will be replaced with an inductor JXT. Two transmission line will be redrawn as two reactance X line 1 and X line 2 in parallel. So before the fault, the electric current will flow from the left hand side to the right hand side, and our equivalent reactance here will be XD prime in series with XD and in series with the two line in parallel. So the total impedance or equivalent reactance will be 0.675 pu. At the receiving end, we know the apparent power already is given as this form, but we also know that it is V bus times the current, the main current, conjugate. And therefore, here we have V bus equal 1 pu, so I equal 0.9 plus J 0.8 conjugate with A 0.9 minus J 0.8 pu. Here we apply KVL to find Vg, and KVL say that Vg equal V bus plus the current times the equivalent impedance here. And then we can find that Vg equal 1.655 with the angle of 0.3757 radian in pu. Notice that here I prefer radian. Therefore, the initial angle here is delta 0 equals this angle, 0.3757 radian. So after finding the initial condition delta 0, which is here, we can. So this is the end of our lecture. For your homework, please practice tutorial 10. And this is also our last lecture for PCT. So please review everything and prepare well for the final exam.